All right, well, thank you very much for the introduction. And Kip Thorne is somebody who needs little introduction. Kip is Caltech's Richard P. Feynman Professor of Physics Emeritus, and he spent his career studying the astronomical implications of Einstein's theory of relativity. Now, if you attended yesterday's beautiful Bacon lecture, you'll know that Einstein himself thought that black holes were just mathematical artifacts of his theory. He didn't really believe that they were real, and it wasn't until Kip Thorne and others picked up these singularities and started asking, could we actually detect them, that we began to investigate their reality. Now, Kip also was one of the troika who founded the LIGO experiment, along with Ray Weiss of MIT and Ron Drever of Caltech, that has been so much in the news lately. And Kip, in the February 11th, when we announced the detection of gravitational waves on Earth for the first time, Kip was described in the New York Times article, which I will note got above the fold, as the evangelist of the field of gravitational wave astronomy. And Kip told me recently that he considers this perhaps his greatest scientific achievement. Now, Kip also is an evangelist for public outreach and for trying to explain science to the public. He's written many books on black holes and wormholes, and recently connected with Hollywood. If you saw Interstellar, Kip was kept them scientifically accurate and wrote a beautiful book explaining the science behind Interstellar. And Kip is going to tell us about 100 years of relativity, from the Big Bang to black holes and gravitational waves. And I will say he wrote this title before the LIGO detection. So my guess is it's not going to be equally weighted towards all three. So my pleasure to introduce Kip Thorne.
Thank you, Fiona. Can you hear me? That's my favorite quote from my friend Stephen Hawking. So I would like to begin by talking about Einstein's Audacity, which leads me into general relativity. In 1687, Isaac Newton gave us a framework for the laws of nature that lasted for 218 years. A framework which is based on the concepts of absolute space and absolute time, on forces, accelerations, things of everyday experience. In 1905, Albert Einstein gave us a new framework for all the laws of physics, a framework that's now been in place for 110, it's now getting to 111 years. He called it the principle of relativity, which says that all the laws of nature must be the same in every freely moving laboratory everywhere in the universe. So this is a law that governs the laws of physics, and that was audacious. If I measure the speed of light, and I get a speed of 300,000 kilometers per second, and you move past me at a speed of 200,000 kilometers a second, and you measure the speed of light, I would ask the question, do you get the difference, 300,000 minus 200,000, so 100,000 kilometers per second? Obviously, our ordinary intuition about how speeds operate would say, yeah, you should measure 100,000, but no, you get the same as I got. And that is a consequence of his principle of relativity. And then you say, how can that be? Something is weird going on with space and time. And indeed, this is possible only because, and this was Einstein's conclusion, from looking at this deeply, you and I, moving at different speeds, disagree about lengths, about times, and even about the concept of simultaneity. So Einstein basically shook up the whole foundations of things that we thought we understood, length, distance, or space, time, and simultaneity. And then he looked at Newton's law of gravity, which says that if you have the sun here and the earth a distance d away, that there is a force by which the sun pulls on the Earth, it goes inversely as a square of the distance between them. And he said, okay, now let's look at that and think about it. The separation d is measured by whom? The sun and the Earth are going to disagree on that separation because they're moving relative to each other. So I'm in a quandary. What does this law really mean? The instantaneous separation is measured by whom? The sun or the Earth? They disagree. And so he looked at that and he said, well, Newton's laws of gravity do not satisfy my principle of relativity, so Newton must be wrong. And that was also audacious because Newton was universally recognized as the greatest mind of all time. And here is Einstein, a young man still, coming out and saying to the world, Newton was just plain wrong. Gravity has to behave differently. And so then his challenge was to find a new way to describe gravity. And so he devised a whole new description of gravity. Jürgen Wren, in his beautiful Bacon lecture yesterday, described in careful detail how Einstein struggled to find his new laws of gravity, and a very interesting struggle and path that he followed. I'm going to give you an extremely simple-minded version of this that is intended mostly to be pedagogical, but it captures two of the key ideas along the way. Let me begin with what I like to call Einstein's law of time warps, though that is not what Einstein called it. Things like to live where they age the most slowly, and gravity pulls them there. Isn't that where you would like to live? And then he gave a mathematical formulation for this. And from that mathematical formulation, one can conclude the following. Well, first of all, the Earth's mass warps time, and the time warp produces gravity. That was one consequence of this idea. That's how our Earth's gravity comes about. And in particular, from the formula that he wrote down, one can infer that on Earth, time must slow by 1 second in 100 years, because that is the amount of slowing that's required to produce the gravity that pulls us to the surface of the Earth. Now, that's not very much slowing. You don't gain an awful lot of extra life by living on the surface of the Earth. But that is enough gravitational pull to produce the enough time slowing to produce the gravitational pull that we experience. And this was, in fact, was verified to a precision of 1 part in 10 to the fourth, 0.01%, way back in 1976. Robert Vassaux at the Harvard-Smithsonian Astrophysical Observatory and NASA flew an atomic clock up in a rocket to high altitude and compared the ticking rate of that clock with the ticking rate of clocks back down on Earth and verified this really was true. Near a black hole, such as Gargantua in the movie Interstellar, I'm going to use Interstellar, for those of you who've seen it, to illustrate several of the concepts in Einstein's general relativity theory. Near a black hole, gravity is enormously stronger, so the slowing of time is enormously greater. And so in Christopher Nolan's film Interstellar, there is a planet that's in orbit around a black hole near the horizon or surface of the black hole. And in the movie, 1 hour on that planet is the same as 7 years on Earth. So that is an enormous amount of slowing of time, made possible by the fact that gravity, or giving rise to the fact that gravity near a black hole is enormously larger than gravity on the surface of the Earth. And so in the movie, you see Cooper, who speaking with his daughter, telling her that I'm going to go out on an adventure, try to save the human race, try to save the world. And I may go near a black hole, and if I go near a black hole, when I come back, much more time may have passed for you than for me. And when I come back from the black hole, you might already be my age. And I may not have aged but a few hours. And so that is what happens. She grows up and becomes a brilliant theoretical physicist. This is one of the reasons I like this movie. And she's trying to solve the problem of gravity. And he is aged 3 hours while he was down near the black hole. And then he goes down near the black hole again and comes back and meets her, and she is a very old woman, and he still has hardly aged at all. And for an audience of 100 million people around the world, Einstein's law of time warps really came to life in this film, and that's one of the things that I and the people who made this film wanted to achieve in this movie, is to get across some of the beautiful ideas, real science ideas, that are in general relativity. Now, in 1912, Einstein realized that if time is warped, then space must also be warped. And that, in fact, was verified again around 1976 by Robert Riesenberg and Erwin Shapiro. They were involved in an experiment to measure the round-trip travel time of radio signals that go from the Earth to a spacecraft, a Viking spacecraft that was in orbit around Mars. Mars carried the spacecraft near the sun, and they monitored the round-trip travel time for the radio signals, and they found that it was not what you would expect if the space between the Earth and the spacecraft was flat. There was an extra delay in the round-trip travel time in microseconds, going up to 200 microseconds, and then back down. And from that, they inferred, well, space has to be, because the speed of light is always constant, the distance that the signal traveled had to be longer than you expected. And so space had to be warped. And you can just infer the precise shape of the warped space. Imagine that the space that is in the plane of the spacecraft and the Earth, and along through which these radio signals are passing. Imagine embedding it in a higher dimensional space so you can look at it and see the warping of space. And this is what we do. As a physicist, I call it an embedding space, or some physicists would call it the bulk or hyperspace. But in interstellar, it's the fifth dimension. You look in the fifth, from what is called the fifth dimension in interstellar, and you see the warping of space in just this form, actually mapped out experimentally with the help of this spacecraft orbiting around Mars in 1976. So in November 25th, 1915, Einstein finally figured out the laws by which the warping of space and time are caused, and it was Einstein's field equation, which I write down here. It's a deceptively simple-looking equation, but it's an equation that contains, once you know the meanings of the symbols in it, it contains basically everything there is to know about classical physics hidden deep inside of here. And it is the foundation then for the things I'll be talking about for the rest of the evening today. This warping of space, governed by that equation, controls the motions of stars, spacecraft, light, and everything else that moves freely through the universe. And I'm going to talk then in this lecture about a few things that Einstein's equation has taught us in the past century. Now, in brief, here is a long list. And if I had all day, I would talk about each and every one of these things. About high-precision experimental tests, about cosmology, the Big Bang, inflation at the beginning of the universe, black holes, neutron stars, pulsars, relativistic objects, geometric dynamics, the nonlinear dynamics of curved space-time, gravitational waves, how general relativity is incompatible with quantum theory and the consequences, speculations about cosmic strings and higher dimensions and wormholes. There's a great richness here. But I only have an hour, and you don't want me to talk much longer than that. And so I have chosen out of all of these topics a hugely rich amount of understanding of the warped side of the universe, I like to call it. Just a few things. And my idiosyncratic choice is topics that involve pure, curved, or warped space-time with no matter present. And so that's what I will focus on. To me, that's the most interesting thing. Black hole is, of course, the quintessential example of something that is made entirely from warped space-time. And so let me begin with black holes. Now, this is a picture of what the black hole would look like if you look in from the fifth dimension, from the bulk, from the higher dimension. You see, if I were to continue this outward, space would become flat, This is the space of an equatorial slice through a black hole, a non-spinning black hole in this case. And so I just take an equatorial slice and then I look at it from this higher dimension so I can see the curvature of space. The horizon of the black hole, the surface of the black hole, such that if you fall through there, you can never get out. The surface is down here, the black region. It looks like a circle, but I've removed one spatial dimension, and so it's really a sphere instead of a circle. If you take a circle and add one dimension, it becomes a sphere. And the thing you notice is that as you go down in here and keep going on inward, circumferences cease to get smaller as you go on in. And so the space looks rather different than what we're accustomed to. I'm showing the slowing of time with color coding. The yellow region is where time is flowing at 10% the rate that it does far away, say back on Earth. And down here at the black region, right at the horizon, time is slowed absolutely to a halt. If time is slowed absolutely to a halt, how strong is gravity? Infinite. And so that is, in fact, then the slowing of time until it absolutely comes to a halt produces the infinite gravity that prevents anything from getting out of a black hole. What makes this warping of space and time? It's the energy that's in the warping of space and time. It's not matter. There's no matter there, no material stuff of any sort. It's true the black hole was created by the implosion of a star long ago. The matter of the star is long since gone, destroyed at the center of the black hole, no longer exists. And so you're left with an object whose warping of space and time has to be created by the only thing that is there, the energy that's in the warping of space and time. It's what we call a gravitational soliton. In Interstellar, Miller's planet, if this black hole is not spinning, it can't be any closer than this, because if it were any closer, the planet's orbit would be unstable and the planet would spiral into the black hole and be gone, be lost. And so it's impossible for Interstellar to be scientifically accurate at all if the black hole is not spinning. But a beautiful thing is, since let me back up, I didn't say enough here. In Interstellar, 1 hour on the planet is 90 minutes on Earth, but up here, the amount of slowing of time is, maybe 0.7 amount of slowing, so a 30% loss of time up there. And so, but if the black hole spins, and as it spins, it drags space into a whirling motion around itself like the air in a tornado, then in fact, the whirl of space stabilizes the orbit, so the black hole can be down very close to the horizon if it spins fast enough. Now, fast enough in this case turns out to be so fast that it's not very plausible that you could have such a black hole spinning that fast in the real universe, but it's possible. It's not ruled out by the laws of physics. And so this illustrates then the concept of the spin of a black hole creating a whirling motion in space like a tornado and what it can do to stabilize things. But Interstellar also illustrates something else, and I'm going to show you a film clip from Interstellar.
How long for the engines, Case?
A minute or two.
Well, we don't have it. Helmets on! Brand, co-pilot, you're up. Case, blow the cabin oxygen through the main thrusters. We're gonna spark it.
Roger that.
Locked! Depressurizing! Engines up!
So you just saw a wave on Miller's planet that is a kilometer high. You don't see kilometer-high waves on the Earth. And so what could possibly be generating it? It's associated with what is called tidal gravity, the same kind of gravity that produces the tides on the ocean. You have Miller's planet near the horizon. Gravity on this side of the planet pulls harder than on that side of the planet because that side is farther away. And as a result, the planet gets stretched. Centrifugal forces are holding it up, and so as in the planet's reference frame, it only feels the average of the gravitational forces. It keeps going around and around, and it gets stretched. And similarly, it turns out it gets squeezed from the side, and this is the same stretching and squeezing as produces the tides on the surface of the Earth, on the oceans. But in this case, it's a much stronger stretching and squeezing. You're dealing with a black hole, after all. And then what happens is that the planet actually has only gotten into this state near the black hole. It's been deposited there somehow fairly recently, as seen by the planet. Now, that may be a long, long time ago as seen on Earth because of that slowing of time. And it's rocking back and forth, settling down into its equilibrium state. The tidal forces try to force the planet to be oriented in this manner. It's rocking back and forth and settling down. And as it rocks back and forth, the oceans slosh, and you do a calculation. And from the sloshing period that you observe of 1 hour between waves, you infer that the mass of the black hole is 100 million times the mass of the sun, and you also can infer that in other ways. There are a variety of things pointing to that in the movie, if you know something about tidal gravity. And gargantuous circumference then is the same as the Earth's orbit. And so there are lovely things you can compute if you know a modest amount about the physics of tidal forces just from looking at the movie Interstellar. Again, rather lovely that you can get this all out in a form that people experience in a movie theater. Now, what does a black hole really look like? Well, if you have a star here and you have a camera, and a star sends light rays to the camera, well, here is one light ray. It's moving along the straightest path that it can in the warped space and time around the black hole. But there's another light ray that goes that way, another light ray that goes down around like this. If you think about it, there are really an infinite number of light rays that can come to the camera, so there are an infinite number of images of each star, most of them very close to the black hole, and then there's going to be a shadow where there are no images. And so we generated then, the team that worked on the movie with me, Double Negative Visual Effects, they generated a movie of what it looks like if you're orbiting around a black hole and you're looking at all those images. And it's rather interesting to see these stellar motions. And we counted a total of 13 images of every star. You see stellar images created in pairs, and then they annihilate every now and then down here near the horizon. Some really wonderful visual effects that occur as a result of what is called gravitational lensing, which is a big deal in general relativity, in astrophysics, and in cosmology. That's not what you saw in Interstellar. What you saw was Interstellar's black hole Gargantua surrounded by hot gas. And this is the iconic image of a black hole now in popular culture as a result of this film. How does that come about? Well, the black hole has a disk of hot gas around itself. We call it an accretion disk. You have a camera that's just a little bit above the plane of the accretion disk that's looking at it. And light ray that comes off the back face of the black hole goes up and over and down to the camera. And that produces this upper piece of the image of the disk. The light ray from the bottom of the back face goes up like that and produces this bottom piece, and then a light ray from the front of the disk goes in and produces this crossbar. So it's all very simple. Again, gravitational lensing, just natural results of the warping of space and time. Where do accretion disks like this come from? I'll show you a movie by a couple of astrophysics postdocs, not at Caltech, James Guillocan and Suvi Jazari. You have a black hole that is tearing apart a star. So a star has gone in, goes around the black hole, and it's torn apart, and all of the insides of the star are thrown out in a big jet. Some of the gas is caught and held and goes in and forms the accretion disk around the black hole. There is a black hole at the center of our galaxy. It does not have an accretion disk, or not much of one. It hasn't been fed recently. Someday it'll get fed and it'll have a nice, rich disk for a while. Andrea Ghez at UCLA and her team have been mapping the orbits of stars in the vicinity of this black hole over a period of several decades. And this is an animation from her team showing precisely what those orbits of the stars are. And you don't see the black hole, but you recognize where it is by following the motions of the stars around it. You see things go into this vicinity, and they swing around. So obviously the black hole is down in here. And it's really remarkable to see this. This is actual then observational data that Andrea and her team have taken. And they show where the black hole is, and from those stellar orbits you can weigh the black hole, and they find that it weighs 4 million times what the sun weighs. A relatively lightweight black hole compared to the one in Gargantua. The one in our nearest galaxy to our own, the Andromeda Galaxy, is 100 million solar masses, the same as Gargantua. Now, there actually are good prospects to see the accretion disk and the shadow of this giant black hole at the center of our galaxy. Radio astronomers are close to this with what is called the Event Horizon Telescope, which combines data from many radio telescopes worldwide. It's a collaboration of hundreds of radio astronomers from 34 universities and institutes. And success is likely in this decade, that is before 2020. So this is really a marvelous thing that we will see something perhaps somewhat resembling the iconic black hole in Gargantua. Not with that kind of resolution initially, but that technology for radio astronomy is so close that we are going to be seeing the dark disk of the black hole and then the accretion disk around it in a few years is really quite remarkable. Inside black holes, there are what are called singularities. We only know this from theory. We've not been in there to discover it. Let me approach this by noting that if you're at the surface of a black hole, hovering there, not falling in, time will stop for you. And so gravity is infinitely strong, so you can't hover there. And then I would ask, what can be slower than stopped time? And the answer is that inside the black hole, you can't hover. Time flows downward toward the center, toward singularities at the center. And once you cross the horizon, you're dragged by the forward flow of time downward. And that's another explanation of why you can't get out of a black hole. This is all predictions of Einstein's general theory of relativity. In Interstellar, Cooper, played by Matthew McConaughey, takes the plunge into Gargantua. Now, I want you to listen. Who's going to talk about crossing the horizon?
I'm nosing down. Approaching the event horizon. Port side, dipping down beneath it to go through it.
So he has crossed the event horizon. He's inside the black hole. And looking above him, you see the hot disk of Gargantua surrounding the external universe is all inside the disk now. You can think about and figure out why its things are turned inside out. But he can see the external universe, but we can't see him. Light can fall into the black hole to bring him an image of what's going on in the exterior. But light cannot come out from him to us in order for us to see him. So another remarkable aspect of general relativity theory. Down inside the black hole, according to theory, there's a chaotic singularity that's governed by the laws of quantum gravity, we believe. It's a singularity that is chaotic, but in which the warping of space-time becomes so extreme that Einstein's general relativity breaks down. We are convinced it has to be replaced by some synthesis between quantum physics and general relativity, a synthesis that is not well understood, but is probably some variant of string theory. And this search for these laws of quantum gravity, probably some variant of string theory, has been the holy grail of theoretical physics since about 1960. And this afternoon, we had John Schwartz, one of the creators of modern string theory, give a talk about that quest in this Bacon conference. These singularities control not only what goes on, the laws of quantum gravity control not only what goes on inside black holes, but they control the birth of our universe. So once we understand the laws of quantum gravity, we should be able to use them to understand how the universe was born. They control whether or not you can build a time machine to go backward in time. There's reason to believe that time machines may self-destruct whenever you activate them. Of course, this is not something we're going to do. But if you were an infinitely advanced civilization, could you do it or not? And, well, Stephen Hawking and I like to make bets, and we have agreed that we can't make a bet on this one because we both agree that it's controlled by the laws of quantum gravity and it's inscrutable until John and his colleagues find those laws. It turns out there are actually 3 singularities inside a black hole. There are 2 that are more gentle than the chaotic one. I'm not going to go into the details, but it is an example of the fact that even Einstein's general theory of relativity, 100 years old, theorists are still plumbing the details of it and trying to understand it in the classical domain before you integrate quantum physics into it. And it's just in the last few years, 2012, that the second of these other singularities inside the black hole was discovered through theoretical work. And so by no means are we finished. In Interstellar, Cooper hopes to learn the laws of quantum gravity from the outflying one of these singularities and use them to save humanity. And this is the climax of Interstellar. For those of you who have seen the movie, you did not understand the climax unless you read my book. And this is by agreement with Christopher Nolan. Chris said in our second meeting in planning the movie, he said, I want to have a ending that's as inscrutable as the ending of 2001, A Space Odyssey by Stanley Kubrick. I greatly admire Stanley. And he said, but I want it to be explainable, and it'll be your job to explain it. And so, anyway. So I now want to move to gravitational waves. I gave a talk similar to this in Berlin on the 100th anniversary to the day of Einstein's general relativity, thanks to Jürgen Wren, who invited me there. And this part was much, much shorter. For obvious reasons, I have gotten rid of 40% of the talk and put in new material because of the discovery of gravitational waves. So I want to spend the rest of my time talking about gravitational waves and their sources, a brief history and a vision toward the future, because this is really a big deal, as I will describe. This begins, of course, with Albert Einstein. 100 years ago this year, I think it was June 1916, he published his first paper predicting the existence of gravitational waves and saying that he thought they were so weak that humans would never, ever discover them. He did not understand black holes as sources for gravitational waves. He did not understand, had no vision for the marvelous technology that we have 100 years later. Gravitational waves themselves are ripples in the shape of space. That's a heuristic way to describe them. I'll describe them a little more carefully in a few minutes. They travel at the same speed as light does. And what they do to things as they pass through them is they stretch and squeeze them. These are tidal forces, the same tidal forces as produce the tides on the Earth's oceans and as distort Miller's planet near a black hole. But tidal forces with a very special form that if the gravitational waves are propagating into the screen, they will take any object, including Miller's planet, they will squeeze it from the sides and stretch it in the opposite direction, perpendicular to the direction the waves are propagating. They don't do anything along the propagation direction. It's entirely in the transverse directions. They squeeze in one transverse direction. In the perpendicular transverse direction, they stretch. The next half cycle, they stretch in this direction, squeeze here, then they stretch up and down, squeeze from the side, and so forth. And the pattern, as time goes on, of that stretch and squeeze is called the gravitational waveform. And these gravitational waveforms from a gravitational wave source are rather like sound. You can take a sound and put it on an oscilloscope and you can see the shapes of the waveforms. These are rather like sound and they carry beautiful information, rather like, think of a symphony, of all the richness of sounds in a symphony and all the information that can be in a symphony. This is similar with gravitational waves. From 1916 to 1966, for 50 years, the first half century of general relativity, physicists struggled to understand the physical interpretation of general relativity. Almost everything I've told you thus far is stuff that we've understood only in the second half century of general relativity. The first half century, physicists, including Einstein, were puzzled. They had a terrible time coming to grips with the theory and how you interpret its predictions and what is physically real and what is just due to you're not understanding the mathematics properly. After all, you're dealing with a warping of space and time, but you understand that mathematically by introducing coordinates. And those coordinates can also be distorted. And what happens if you just have coordinates distorted and there's no real true warping of space and time? It's only coordinates, and that caused enormous confusion. A variety of other things caused confusion. And it took a half century to sort this out, and during that half century, black holes were predicted. Einstein didn't believe the predictions because he didn't understand the predictions of his own theory. He didn't understand what was really physical and what wasn't. Einstein himself predicted gravitational waves, and then he had second thoughts, and then he clarified it, got his mind cleared again, and then he had second thoughts again, and he went back and forth. And so it was a real rough period. Fortunately, I entered this field in 1963, just as the tail end of that was happening, and when an understanding was in place adequately that we could begin to think seriously about astrophysical applications, the things that I talked about, and actually searching for gravitational waves. And it was Joseph Weber in the 1960s at the University of Maryland who did perform the first searches for gravitational waves. He had the audacity to think that it might be possible to discover gravitational waves, despite Einstein saying that it was unlikely that they could be found. And he went forward then and built detectors. He did not see them in the end. He thought he had for a while, but it turned out he hadn't. But in 1967, Ray Weiss, who had been a friend of mine at Princeton when he was a postdoc and I was a graduate student in the early 1960s, he went to MIT and started thinking about gravitational wave detectors of a different sort. And in 1972, he laid down this new kind of a design for a gravity wave detector in enormous detail. And this is what became the LIGO gravitational wave detectors, or an earlier version of them. It was improved in some ways, as I'll describe in a moment. It's a remarkable paper, technical paper he wrote, published in April 15th, 1972. In this paper, he said he examined all of the noise sources that such a gravity wave detector would have to face, and he explained ways to deal with each and every one of the noise sources and estimated how big the noise would be after you dealt with it, and therefore how good the gravitational wave detector could be, and concluded with a gravitational wave detector that has a size of a few kilometers, you had a chance, a fighting chance to see gravitational waves. And it is a real remarkable paper, but he didn't publish it in the regular literature. It was published in an internal MIT report because he believed at the time that you should not publish something like this until you've seen gravitational waves. And so he's ready to publish now. In 1972, Ronald Drever in Glasgow got into this business, first with Weber's technology, and then when he saw Ray Weiss's design and thought about it, he switched over to Weiss's approach, and he invented some very important improvements on Weiss's design that led ultimately to this kind of a scheme. So what you have is mirrors that hang from overhead supports, and the gravitational wave pushes these mirrors apart and pushes those together, then pushes these apart and pushes those together, and you use a technique called laser interferometry to monitor that changing difference in arm length. And I won't go into the details. Ray Weiss had this light beam coming in, bouncing back and forth many times, 100 or 1,000 times between the mirrors, making discrete spots on the mirrors. Ron Drever said, no, let's have all the beams overlap, And they're just trapped in here by high reflectivity mirrors, and this is what is called a Fabry-Perot cavity. That was one of Ron's improvements. That it looked to be much more difficult, but Ron showed that, in fact, it was possible. He built a prototype and did succeed with this alternate scheme. But it was basically a variant on top of what Ray had come up with. 1967, I came to Caltech. Ray went to MIT. And I built a group working on the theory of gravitational waves and the theory of their sources. And by 1976, and I began to develop a vision for the science that could be done by these kinds of gravitational wave detectors. By 1976, in talking in depth with Ray Weiss and with a Russian colleague, Vladimir Braginsky, I became convinced that gravitational wave detection was likely to succeed, and I wanted Caltech to be involved. And so I made a proposal to Caltech that we build an experimental group to do this. It was embraced enthusiastically by the faculty, by the administration, the president, the provost, and I was even brought out to talk to the trustees about it in this early phase. And they didn't have to approve something like this, but they were very enthusiastic. So the community embraced this, and we never turned back as a community. Caltech has been an absolutely wonderful supporter of this effort. We brought Drever to Caltech to lead the experimental effort. And now I'm going to give you some numbers for what we understood we were dealing with. By 1978, we knew approximately how strong the strongest waves would be that are bathing the Earth. I and others had done enough on the theory of sources to know we needed a strain of delta L divided by L. These mirror separations change by an amount delta L. You divide it by their actual length. And that's what we call the strain. And the estimate was that we had in 1978 was 10 to the minus 21 would be where pay dirt is. The gravitational waves that were discovered, the announcement made precisely 1 month ago, the strength of those waves was 10 to the minus 21. It was right on the money of what we were, we set up. We even had T-shirts at this conference where we agreed on what is our goal, 10 to the minus 21 or bust. This is 1978. 78, that's basically 40 years ago. 78, 88, 98. That's the only way I can do math. 40 years ago. Okay. But then you look at what that means delta L is. If L is 4 kilometers, which is what we wound up with, and we knew before that we would be dealing with something like that size, then delta L is about 10 to the minus 15 centimeters, which is the diameter of a proton or an atomic nucleus divided by 100. Well, that's 10 to the minus 11. That is 10 1/trillionths of the wavelength of light, and you're using light to try to make this measurement. And people looked at that and they thought, this is ridiculous. And I looked at that when I first heard about it, and I thought it was so ridiculous that I wrote a little sentence in a textbook, a classic textbook that I co-authored called Gravitation with Charlie Misner and Johnny Wheeler, which said, it seems unlikely that this is ever going to work. And then I spent much of the rest of my career trying to help the experimenters make it work. Because I looked in depth at Ray's analysis of 1972, and I saw it is feasible, but it's going to be extremely difficult. My close Russian friend, Vladimir Braginsky, who I think along with Ray is one of the really great experimenters I've ever known, he looked at it and similarly said, this is so difficult that it's unlikely ever to succeed. And he continued to push the kind of gravitational wave detection technology that Joseph Weber had pursued for 10 more years. Then he came in and saw the progress that had been made with a prototype that I'll talk about at Caltech. He went back to Moscow, shut down his whole experimental effort, and joined our effort. But for 10 years, he didn't believe it. It's so complex, so difficult experimentally. So Ron came to Caltech. We got funding from the National Science Foundation to build a 40-meter prototype detector led by Ron and Stan Whitcomb, shown here, who was brought in along shortly later than Ron in 1980 as an assistant professor. He's now the chief scientist of the LIGO laboratory. He and Ron led the construction of this 40-meter in the period 1980-83. And in parallel, NSF funded Ray Weiss to continue work on his smaller prototype, but also to do a feasibility study for kilometer-scale interferometers. Could you really build them, and what would be required to build them? And Stan Whitcomb participated in this MIT feasibility study. And in 1984, we came together, we went to NSF, and we presented the results of the feasibility study, the achievements of the prototypes at Caltech, at MIT, and 2 prototypes in Europe, in Glasgow, Scotland, that Ron had started, and in Garching, Germany. And together with NSF, we created what we called the LIGO project, Laser Interferometer Gravitational Wave Observatory, run initially by a troika, as Fiona said, of Weiss, Thorne, and Drever. Now, troika in that era was a sort of disreputable name for a dysfunctional leadership, and that was an understatement about our leadership. We were told in no uncertain terms at the end of 1986, if you want to do this, you have to get a strong single leader. And so we brought on, with the help of the Caltech and MIT administrations, brought on Robbie Vogt, a strong single leader, who knocked heads together between the 2 experimental teams and made them really merge together and work together very effectively. And then led us in the writing of a construction proposal that had a vision where we would first build facilities, vacuum system and so forth, in which these interferometers would operate. And then we would have a 2-step or 2-stage strategy. We would build initial interferometers at a sensitivity where we would have to be awfully lucky to see anything. And then, having gotten the experience with the initial interferometers, move forward with advanced interferometers that were in the region where pay dirt should be. Initial interferometers getting, but not quite, to 10 to the minus 21. Advanced interferometers pushing down toward 10 to the minus 22. And so that was the proposal we put in. And then we ran into a buzzsaw. This was being funded out of NSF physics. It was being done by physicists for whom this is a natural approach. You look, you see what's required. You know that with your current experience and technology, you have to do it in 2 steps to have a success-oriented strategy. But our ultimate goal was to do astronomy. And there were a number of eminent members of the astronomy community who just could not accept the idea that you build something that's not going to see anything with high probability. And then you build something else after that. And building the first step is $300 million. $300 million will build with $300 million, you can create a fabulous optical telescope, or several. And so we got blindsided, Robbie got blindsided in congressional testimony by eminent astronomers, and we had a royal battle politically. NSF and Caltech and MIT stood by us firmly. It was not by any means all the astronomers. It was a number of very eminent astronomers, but there were many in the astronomy community who backed us, who accepted this vision. And after 2 years of struggle, Congress bought in, and they have stood by us all the way through since then. So you have to hand it to Caltech, to MIT, to NSF, and to Congress once they had bought in. It's been a long haul from then to here. This is early 1990s. Let's see, 2000, 2010. That's 25 more years, okay? In 1994, I just lost my laser. No, I haven't. Barry Barris was brought on as director. Robbie Vogt had what he liked to call a skunk works operation. He had a management plan for this, which was very lean, and NSF was very concerned and felt this was not sufficiently success-oriented. They wanted a much more robust management. And so Barry was brought in. And he was the real genius who created the modern LIGO. He was the director of LIGO from 1994 to 2005. He reorganized LIGO's planning completely. He oversaw the construction of the vacuum facilities. Once the facilities were nearly completed in 1997, he said to Caltech and MIT and all the experimenters, we have to expand. We don't have nearly enough manpower and the right kinds of manpower to pull it off ourselves. We will create something called the LIGO Scientific Collaboration, which will bring in scientists from many other institutions around the world in order to pull this off in the end. And so it got expanded to other institutions so that today we now have the facilities in Livingston, Louisiana. We have the facilities in Hanford, Washington, and this LIGO Scientific Collaboration is now a collaboration of 1,000 scientists at 75 institutions in 15 nations around the world. And this is the list of nations. And so it's a huge transformation. In 2000 to 2005, we ran initial interferometers in the vacuum system, installed the initial interferometers in the vacuum system, brought them down to design sensitivity, and carried out the first searches. And then Barry, who many people have said to me, he's the most brilliant leader of large projects that physics has ever seen, he was stolen away to lead the design study for something called the International Linear Collider, which is a collaboration of all of the major countries in the world. And he was told by his colleagues and by the leaders of funding agencies in these countries that if he didn't do it, it wouldn't get done because they couldn't agree on anybody else to do it. And so he left LIGO. Fortunately, we had a series of other directors, Stan Whitcomb as acting director for a year and a half, Jay Marks, David Wrightsey, who took over and led us through the subsequent period of searches with the initial interferometers, installing the advanced interferometers into the vacuum system, and then the detection of gravitational waves at the end of that installation, which I will get to in just a moment. Before I get to that, however, I want to describe something from my own personal point of view. I had a very big worry in 2001, and the issue is we would not be able to understand the gravitational waves we see. We would not be able to extract all the information they have in them unless we could do computer simulations with our sources. Colliding black holes is the principal example. We could not solve Einstein's equations to learn the details of a collision of a black hole. It was just too hard a problem. You couldn't do it with pencil and paper. The only way you could do it was on a computer. And there were a number of people who had been working on this nearly as long as people had been working on LIGO, and they were stuck. And so I left LIGO. So the great success is really to be attributed to the superb team that I left behind, particularly the younger experimenters who really pulled this off. But I went over and I put together a collaboration with Cornell University, Saul Tukulski there, initially Caltech and Cornell, to simulate black hole collisions or simulate extreme space-times, as we called it, the SXS collaboration. It's now expanded to a number of other universities. So it's a LIGO-like effort, but much smaller. There are something like 50 people in this collaboration. There are 1,000 people in the LIGO collaboration. A 15-year effort. We now have the tools are all there, and there are several other research groups who also are able to do these simulations, but not nearly as rapidly on computers or as accurately. We are carrying out about 1,000 simulations to underpin the LIGO data analysis, extracting information from the sources and searching for sources. We begin with a black hole that has some spin along this direction with this speed of spin proportional to the length of the arrow, another smaller black hole orbiting around each other. They collide and merge, and we compute the gravitational waveforms that are emitted, and those are used in the LIGO data analysis to underpin the LIGO data analysis. So I'll now turn to the discovery, which involves, of course, primarily the experiment, but also involves the simulation feeding in. And I'm going to first tell you what we saw and then how it is that we know this is what we saw. So this is the bottom line for what we saw, the LIGO team saw on September the 14th of last year. 1.3 billion years ago, in a galaxy far, far away, 1.3 billion light years away, two black holes were orbiting around each other, and this is the same kind of a simulation as we did for Interstellar, done independently. I was simultaneously tied to the double negative visual effects people doing the simulation for Interstellar at the same time as these simulations were being done by the SXS collaboration. There you see the black holes going around each other. It's a beautiful display of gravitational lensing as they go around each other. They're going to collide and merge into one black hole, and they're getting close. The collision and merger is extremely violent, but you don't see the violence so much in this movie. The collision has occurred, it's ended, gravitational waves were emitted, and they're traveling to Earth. To really see what was going on, you have to go up into a higher dimension, go up into the fifth dimension, look in on the warped space in the orbital plane of the black holes. Here are the black holes, these funnels. The color coding, as before, represents the slowing of time. In the yellow region, it's 20 or 30% slowed. In the red region, down inside here, it's horrendously slowed. And the arrows are the dragging of space into motion, like the whirling motion around a spinning black hole. And this is the gravitational waveform that is being emitted. You see the blue point is where it is on the shape of the waves of stretching and squeezing. The orbit precesses because of the dragging of space into motion. We're going to pause it just before the collision and go into slow motion. And we're going to watch the warping of space become very extreme, end of time become very extreme during the merger. I'll pause it completely at the moment of merger. That's what it looks like at the moment of merger, tremendously warped space and time. It has created a veritable storm in the structure of space and time during the collision. It's a brief storm. But during that storm, gravitational waves were emitted that carried off 3 solar masses of energy. It's like taking 3 suns, converting them entirely into energy, and putting that all into gravitational waves. That all comes off, most of that comes off in a time of a small fraction of a second. And so the power output, the energy per unit time, is really high, 3 solar masses of energy in a fraction of a second. It is 50 times larger power than the total power output of all the stars in the universe put together. 50 universe luminosities, none of it coming out in electromagnetic waves. No light, no X-rays, no radio waves. It's all in gravitational waves. And it has traveled across the universe, 1.3 billion light years, and reached Earth. And it has now so weak that it stretches and squeezes things by 1/100th the diameter of a proton in the gravity wave detectors. Strain of 10 to the minus 21. Those gravitational waves arrived at Earth on September 14 from the southern hemisphere. They passed through the Earth unscathed, and then through the gravity wave detectors almost unscathed. Arrived at the detector in Livingston, Louisiana, coming up through the Earth. 7 milliseconds later, arrived at Hanford, Washington, coming up through the Earth, stretching and squeezing along those arms, stretching and squeezing the mirrors in those arms. The data, the strain, the delta L over L, this is in units of 10 to the minus 21 at Livingston, Louisiana. This is the raw data. We expected you wouldn't see it by eye in the raw data. You'd have to dig into the noise. All that's done here is to do what's called a band pass, throw away everything above 350 hertz and throw away everything below 35 hertz. And so it's a little jagged, basically, because of the way that that filtering has been done, that tiny amount of filtering. But you see it's jiggling around, and then it goes into large-scale oscillations and then dies out. Here it is at Hanford, Washington. Let's overlap the two. Well, first, this is the theory, what the simulations say the waveform should have looked like. And they agree beautifully once the waves get strong. And here's the overlap of the waves from the two sources, a beautiful overlap when the waves are strong. And so what was done was to go in and compare the shapes of the waves that were observed with the predictions from simulations. There are a number of intermediate steps. The data analysis is very complicated, but this is basically what was going on. And picked out the particular black hole pair that agrees best with the observed waveforms. So two black holes, one is 29 times the mass of the sun. The other is 36 times the mass of the sun, and a total of 65 solar masses. And the final black hole is 62 solar masses, and 3 solar masses has been radiated as gravitational waves. And you can infer the distance to the source, because knowing what those masses of those black holes are, you can then go out and you then know how strong the waves were at the source, and so they've weakened as they came to us, and you can infer the distance 1.3 billion light years. Just a beautiful, beautiful verification of Einstein's theory. So I'm going to conclude with just a few words about the future and then take a few questions. We'll see a lot of other sources of gravitational waves with LIGO. We'll see spinning neutron stars called pulsars. We'll see black holes tearing neutron stars apart. These neutron stars have masses of the sun. They have densities of 10 times that of an atomic nucleus. They have sizes that are smaller than Pasadena. So a black hole tearing a neutron star apart. 2 neutron stars colliding and merging. Supernova explosions, aside from colliding black holes, the biggest explosions that astronomers have ever seen, except the Big Bang. The cores of supernova explosions, we don't know much about them, but the gravitational waves will be emitted, and when we see those gravitational waves, we'll be able to start to decipher what goes on in the core of a supernova. There is reason to suspect that the fundamental strings that are building blocks of all matter, according to the laws of quantum gravity, that some of them were expanded to cosmic scale in the early inflationary phase of the universe. And then when they collide with each other, they reconnect, make cusps, bends in the strings, and those bends emit gravitational waves as they travel at the speed of light. And so we could have the first tentative verification of string theory. There's a lot of ifs, ands, and buts along the way, but beginning to do some very esoteric and exciting science there. And above all, there are bound to be huge surprises. There always are when a radical new window opens onto the universe. But it's not just one gravitational wave window, it's 4 gravitational wave windows. Just as we think of optical astronomy as being one window on the universe, radio astronomy is another, X-ray astronomy is another. Those are all based on electromagnetic waves. Gravitational waves, LIGO looks for gravitational waves with periods of milliseconds. Something called LISA, which is 3 spacecraft that track each other with laser beams, will look for waves with periods of minutes to hours. Pulsar arrays of pulsars in the sky, when the radio waves from these things come to Earth with very precisely spaced pulses, if a gravitational wave sweeps across the Earth, it slows our clocks down, then speeds our clocks up. And so all the pulsars synchronously will appear to speed up and slow down because our clocks are being affected by passing gravitational waves. Those are waves with periods of years to decades. And then something called the polarization of the cosmic microwave background has the expectation of seeing waves with periods of millions to billions of years in the form of patterns on the sky. These 4 windows onto the universe, well, one is open today, 2 more are likely to be open in the next 5 years or so, and the third in the next 15 or 20 years. So it's as though we got optical astronomy, radio astronomy, X-ray astronomy, and infrared astronomy all over a period of 20 years. This is just the beginning. So to conclude, the first 100 years of general relativity were amazing, but the next 100 years with gravitational wave detection and the issue of the laws of quantum gravity, trying to understand the birth of the universe, those are going to be more amazing. Thank you.
Yes, well, it's too bad that Einstein couldn't have been around to see his 100th birthday present. But we have time for a few questions, and I will take them over here. Kip?
No, one question per person initially. If the other people don't have any questions, then we'll give you as many as you want.
Well, when you talked about how something goes through a black hole, 2 more singularities are generated. Do you know much about how they're generated? And is that beautiful SXS simulation available online?
That was 2 questions, but I'll answer them both. Yes, the SXS simulations are available online. Go to blackholes.org, which is the SXS website, and you'll find lots videos from lots of simulations. Excellent question about these 2 other singularities inside black holes. The one of them is a singularity when you go into the black hole. The singularity comes crashing down on top of you. And so you don't want to slow down as you fall in, or it'll hit you. And that singularity is caused by a weird thing about time. I told you that time slows down near a black hole. Well, it's slowed down so much in such an extreme way inside the black hole that all of the stuff that's going to fall into the black hole over the entire future of the universe comes crashing down on you in a fraction of a second. It's billions of years to come in as seen on the outside, but it comes smashing down on you in a fraction of a second, unless you move fast enough that it doesn't catch you. And there's the other one comes up from below, and that's all the stuff that fell into the black hole before you did. A little bit of it backscatters toward you, a tiny bit, and that all comes crashing up at you in a fraction of a second. And this was discovered using what's called perturbation theory on what's called the Kerr metric. So it's mathematical physics, but I think it's fairly reliable. I wouldn't regard it as totally reliable until we have computer simulations of this, which we don't yet have. Occasionally, these kinds of approximate analyses can go wrong. So I am looking forward eagerly to future computer simulations.
Was it just luck that the thing was on when these waves passed, or or if it's on all the time, can you detect waves all the time?
So I should re-emphasize that it's not me. It's a superb team that I have been attached to, and that I have not been involved much since the early 2000s, except for getting the simulation work started. So this superb team had turned on these detectors. Let me start over. So the detectors, they finished installing the detectors in the first of the detectors in something like May of 2014. And then they put light in the detector and started bringing it down toward design sensitivity. And by early in 2015, they had reached a level of about 1/3 of their design sensitivity, 1/3 of the sensitivity we said we would get. That was already 3 to 4 times better than the initial detectors. That meant that the detectors at that point, which is early last year, the first of these detectors could see out through a volume of the universe that was 3 or 4 cubes, say something like 40 times larger volume of the universe than the initial detectors could. So a huge, huge, huge improvement. The second detector, which was always coming along a little later, you bring the first detector on and get it going and bring the second detector on. By summer of last year, it was also at that level. And so then the team geared up to do its first gravitational wave search, which was scheduled to begin around the middle of September. The team was just a few days away from starting that search and was in what is called an engineering mode, which was basically making sure that everything is okay, that the detectors are tuned in the manner that you want them tuned, So basically ready to start a few days later, and the gravity wave came in. And there were people who were there that night, and they were still working on doing various kinds of tests and so forth. And they shut down their tests because they got tired and decided we'll come back in the morning. And so, fortunately, because if they were performing tests when that signal came in, you couldn't have known whether or not it was a real signal. So, yeah, it was kind of lucky.
Okay, with that, there is coffee, I understand, outside, and so you'll have an opportunity to informally ask some more questions. But let's thank Kip again for his lecture.